Hello, my name is Dr. Eric Gossett. For 35 years, I taught mathematics and computer science at Bethel University in St. Paul, Minnesota, USA. Many of you, I'm sure, were disappointed when the 2020 WMI final contest in Malaysia needed to be canceled because of COVID-19. Fortunately, WMI has organized some replacement local and regional contests that should occur during October of 2020. I hope that you enjoy this following short video. You may have wondered what happens if we start adding numbers and just keep adding more and more numbers. If we add 1 plus 2 plus 3, we get 6, which is larger than 1 plus 2. If I add a 4 onto that, we get larger at 10. If we add a 5 on the end, we get even bigger. So we assume that this is going to get bigger and bigger and bigger as we add more and more numbers. Some of you may recognize the sums as an example of the famous set of triangular numbers. The triangular numbers were named because if you add these numbers and represent them by little dots, 1 plus 2 forms a little triangle. If we add 3 more dots, we get a bigger triangle. If we add 4 more dots to that, we get an even larger triangle. Some of you may recognize this configuration as the pattern that we use to set up bowling pins in the game of bowling. Almost 700 years ago, a mathematician named Oresme was born, actually in 1323, and he started studying these infinite sums. One of the sums that he studied resulted in something that we call the harmonic numbers. He was interested in the sum 1 plus a half plus a third plus a fourth plus a fifth, and just going on forever. Now, in order to represent these long sums, mathematicians nowadays use a shorthand notation called summation notation. And the nth harmonic number is defined to be the sum k equal 1 to n of 1 over k. This notation says use the pattern 1 over k and let k take on the values from 1 to 2 to 3 all the way up to n, and substitute the current value for k. This Greek letter sigma says that we should add the results. And so when we have k equal 1, we get the number 1 over 1. When k becomes 2, we add 1/2 with a plus sign in between. Then we move k up to 3, and we keep going until k equals n. We substitute n in for k and quit. So, for example, H4 would be the sum k equal 1 to 4, 1 over k. And that gives us 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. So the question is, what happens if we add more and more of these? Well, it seems like we're adding a positive value to each previous sum, so it ought to get bigger. But the things that we're adding become smaller and smaller and smaller. By the time n equals 1 billion, the number we're adding is very small indeed. And so the question is, how big can this get? Well, Oresme was the first to prove that this collection of numbers hn grows and grows forever. When n is 10, we add 1 up through 1/10, we get a number slightly less than 3. By the time we've added up 1 billion of these numbers, we're only at 21, a little over 21. And so this sequence grows very, very slowly, but Oresme was able to prove that it does grow forever. As long as you keep adding more, you'll get larger than any number you can think of. Well, this wasn't the only sequence that he considered. He also thought about this sum. What if we add 1/2 plus 2/4 plus 3/8 plus 4/16 and just kept going forever? What we notice is that each numerator is one more than the previous one, and each denominator is 2 times the previous one. 16 is 2 times 8. If you don't know how to do multiplication yet, you can still use addition. 8 is 4 plus 4. 32 is 16 plus 16. Now what we notice is that the individual numbers in this follow a pattern. It's an integer k divided by 2 multiplied by itself k times. The notation 2 to the k means multiply 2 times 2 times 2 k times. So for instance, 2 cubed is 2 times 2 times 2, which is 8. The sum that he was interested in then starts growing from sums that look like k equal 1 to n of k over 2 to the k. And we can experiment as we let n get bigger and bigger and bigger. We can experiment with this. Oresme didn't have a calculator back in 1350 or so when he was working on this, but we do. We can start adding these numbers more and more on a calculator, or we can use some software to simulate what happens. So when n is 1, I get an answer of 1/2. When n is 2, I get 1/2 plus 2/4, which has value 1. Adding 3/8, I get 1.375, and we can keep going. And what we notice is that when I've added 8 of these, I get 1.96. Add one more, I get a bigger number, 1.978. What happens if we were to add the first 50 of these? What we get is a number that's very, very close to the number 2. And so we might guess that this sum, as we add more and more and more, gets closer and closer to 2. In the summation notation, we use this symbol, the infinity symbol, which looks like an 8 on its side, to represent the instruction to tell us to keep adding and adding and adding and never quit. Infinity is not a number, but it is an indication to us that we should just keep adding these numbers forever. But this guess is not a proof. It's possible that this collection of numbers will behave like the harmonic numbers and just keep getting bigger and bigger and bigger, but just doing so very, very slowly. It's also possible that this gets closer and closer to some number that isn't 2. So how do we prove our guess or something like it? Well, Oresme had a very clever way of doing that. He used his imagination and a picture to actually prove that this is equal to 2. What he did was he started with 2 1-by-1 squares. And then he wanted to start subdividing the second square. Now, in order for us to see what he was doing in his imagination, I'm going to stretch these 2 squares in the horizontal direction, but we still want to think of these as being 1-by-1 squares. So each one has area 1. What Oresme did was that he cut this second one in half and then cut the right-hand piece in half again, and he just kept imagining doing that forever. So we have a piece here we'll label alpha that has area 1/2. This piece labeled beta has area 1/4. It's half of the remaining half. Gamma has area 1/8, delta 1/16, and this just goes on forever. Next, Oresme decided to build a stack, a tower. He imagined putting the piece labeled alpha on top of the right-hand side of this square and then putting beta on the right half of the next level and just doing that forever. And when he does that, we have to use our imaginations a little bit and imagine this picture just growing and growing forever. This piece would be cut in half, and the left-hand piece would be put up on top of that. and this would then go through the screen, past the clouds, past the moon, and go forever. Now, Oresme then started thinking about this. This is a square on the bottom with area 1, and the rest of the tower going on forever came from a square that also had area 1, and so the total area of this tower must be equal to 2. Then he did something very clever. Instead of thinking about these blocks horizontally, he decided to think about them vertically. And so he looked over on the left and he says, I have one block of area 1/2. I get some additional area from these 2 blocks of area 1/4, so I need to add 2/4. Then there are 3 blocks of area 1/8, so we add 3/8. 4/16 for those 4 blocks, 5/32 for the next 5 blocks, and that goes on forever. And so if he looks at it vertically, he has this infinite sum, which was the sum he wanted to study. But he already knows that the area of this tower is 2, because it was formed out of 2 1-by-1 squares. What this means is that Oresme had successfully proved that the sum of that infinite sequence of numbers, 1/2 plus 2/4 plus 3/8 and so on, actually equals to 2. I hope that you continue to enjoy learning and doing mathematics. I have one more thing to show you before I say goodbye. Nicola Oresme came very close to inventing the game of Tetris. Thank you for watching. Goodbye.